Welcome to the deep dive. In an era where crime and even just complex accidents are getting so much more complicated, we can't just rely on what people remember seeing.
Absolutely not. An eyewitness account is, well, it's notoriously unreliable. The stakes are just too high.
So our mission today is to do a deep exploration into forensic science. This is that critical discipline right at the intersection of hard science and the search for justice. We're going through the foundational documents to pull out the principles, the feels, and the actual techniques they use to prove facts.
And if you want a really simple definition, just think of forensic science as taking everything we know about how the world works, chemistry, biology, physics, and putting it to work for a judge and jury.
So it's about solving problems, enforcing the law.
Exactly. And proving facts, whether that means finding the guilty person or, just as importantly, proving someone is innocent.
Okay, so when most of us hear forensics, our minds immediately go to, like, a TV crime lab. But the sources make it clear that this field it's massive. It's not just one thing.
Not at all. It really splits into two huge categories. First, you have the natural sciences, which is your basic crime scene investigation, or CSI, collecting physical evidence.
And boots on the ground.
Right. But then you have the applied sciences, and this is where it gets incredibly specialized.
Let's maybe look at a few examples because they sound like completely different jobs.
They really are. Okay, so first, take forensic odontology.
Dentistry.
Exactly, yeah. It's the use of dentistry in the justice system. And you might think, well, we have DNA now, but what happens when a body is severely compromised? A fire, a plane crash, advanced decomposition.
There's no soft tissue left.
Right. But teeth, fillings, dental structures,
Yep.
they often survive. So comparing dental records and x-rays to the remains is sometimes the only way to confirm an identity.
Wow. So those fillings you got as a kid could end up being your final signature. That's an incredible level of data.
It is. Then you have something totally different, like forensic engineering. This is all about applying math and physics to legal cases.
So not just criminal stuff.
A lot of it is actually for civil cases, yeah. They're the ones who figure out why an industrial product failed and hurt someone. Or they'll calculate the cause and the spread of a fire or an explosion. They bring the hard numbers to the courtroom.
And then there's the one that always, captures everyone's imagination. The gruesome one. Forensic entomology.
Yes. The study of insects.
On a corpse.
On a corpse, yes. It's not just about what bugs are there. It's about their life cycles. Different species show up at different times, and their development from egg to larva is incredibly predictable based on the environment and temperature.
So the bugs are like a tiny, gruesome clock.
That's a great way to put it. An entomologist can analyze the stage of the insects and pin down the approximate time of death with remarkable accuracy.
So you have all these different complex sciences.
Yeah.
What's the one truth that ties them all together? There has to be a foundational idea.
There is. It's called Locard's exchange principle. It's really the axiom of all modern forensics.
And what is it?
It's deceptively simple. Every contact leaves a trace.
The moment two things touch, they swap a little bit of each other.
Yes. And that has this huge implication. A perpetrator can't enter a crime scene without leaving something of themselves behind and taking something of the scene with them. It could be fibers, hair, sweat, soil. The scene itself becomes a witness.
How does that change the mindset for an investigator?
It shifts everything. Instead of just relying on what someone says, you start analyzing what was exchanged. The saying goes, evidence never lies. The evidence is neutral. It doesn't have a motive. It doesn't forget things.
Wait a minute. You say evidence never lies. But what about human error? What if an investigator sneezes on something or drops a hair? That evidence isn't lying, but it's misleading.
And that is the central challenge. You've hit on why protocol is everything. The physical evidence itself is objective, but its value can be completely destroyed by bad handling.
Okay.
Which is why we have the chain of custody. This is the crucial rule.
The unbreakable chain.
It has to be. From the second that evidence is collected until it's in the courtroom, every single person who touches it, every place it's stored, it all has to be documented. Any gap, any break in that chain, and the defense can argue contamination. It can render the evidence worthless.
So that's the human safeguard on Locard's principle.
It is.
All right, so once the evidence is secured, let's get into the cool part. How does science turn a tiny protected trace into a person? Let's start with the gold standard. fingerprints.
Okay, so fingerprints operate on the law of individuality. No two are alike, and they're formed in the womb and never, ever change. They're made of the raised parts, the ridges, and the grooves, the furrows.
And they fall into three main pattern types.
Yep, the arch, the loop, and the whorl, which actually has 5 different subtypes. But the real challenge isn't the pattern itself, it's collecting the print in the first place.
And I'm guessing some are easier than others?
Oh, definitely. You have your visible prints. Those are the easy ones. A bloody handprint on a wall or an impression left in soft putty. The real work is finding the latent prints.
The invisible ones. Just sweat and oil.
Yeah.
So how on earth do you lift something you can't see?
It depends entirely on the surface. For something smooth, like glass or metal, you use a fine powder that sticks to the residue. But if you try that on paper, you'll just ruin it.
So what do you do for paper?
That's where chemicals come in. You might use something like ninhydrin, which reacts with the amino acids in the sweat and turns the print a purplish color.
I always found the technique for things like leather or plastic fascinating. Something about superglue.
That's right. It's called cyanoacrylate fuming. You put the object in a sealed chamber, you heat up superglue, and the fumes actually bond with the print residue. It polymerizes and turns the print into a hard, white, visible pattern.
That is incredible. And once you have that print, you feed it into the big system.
Into AFIS, the Automated Fingerprint Identification System. It's basically a giant digital library. It scans the print, maps out all the unique points, and compares it against millions of records in minutes. It's a game changer.
But what if you don't have fingerprints? The sources point to some other really unique identifiers, like the human ear.
It's true. The cartilage structure of your ear, all those curves, the helix, the tragus, it's completely unique. And like a fingerprint, it doesn't change from birth to death. Biometric systems that measure the ear can get an identification accuracy of up to 99.6%.
99.6%. Wow. Just from the shape of an ear?
And for cases with skeletal remains, there's skull analysis. An expert can look at a skull and determine sex with high-accuracy male skulls tend to be larger, rougher, with a more pronounced brow ridge. They can even estimate ethnicity. It helps narrow down the search immensely.
Okay, let's put this all together. Let's look at how these rules and sciences actually work in the real world under pressure.
A great first case is one that shows how forensics can overcome someone trying to actively destroy evidence. The Japanese curry poisoning in 1998.
The story is just horrifying. Arsenic in a curry pot, 4 people dead, dozens sick. What was the challenge for investigators?
The suspect, a woman named Mrs. Hayashi, was meticulous. Her husband worked for a pest control company, so she had access to arsenic. She cleaned the crime scene so well that the standard lab tests, they found nothing. No arsenic residue on the curry pots at all.
So it looked like the evidence was just gone.
It looked that way. But the forensic team just couldn't accept that. They believed traces had to be there, even if they were too small to detect normally. So they took the pots to a high-level lab, a synchrotron research institute.
What does that do?
It's basically a particle accelerator. It lets you analyze materials at the molecular level. And by doing that, they found it. Tiny trace amounts of arsenic still bonded to the metal of the pots. That was the physical evidence that led to her conviction.
That's science refusing to give up. Okay, our next example is all about the power of numbers. The hit and run involving Warrior Uvidia in 2012.
This was a classic he said, she said, but with physics. The driver claimed he was only going maybe 70 to 90 kilometers per hour, and that the victim swerved in front of him.
So how do you prove that wrong?
An expert witness didn't care about testimony. He looked at the physical evidence, the skid marks, the vehicle damage, the impact angles, and he applied physics equations. The calculations showed the car's actual speed was about 177 kilometers per hour.
Double what he claimed. That one number completely destroys his story.
It does. And then there was the toxicology.
Right.
The blood tests found 2 substances, benzoyligurine and cocathylene. Now, it's really important for you to understand these aren't the drugs themselves, they're metabolites.
The chemical footprint left behind.
Exactly. Benzoyligurine only forms in your body after you've used cocaine, and cocathylene only forms when you mix cocaine and alcohol. So even if the drugs themselves were gone from his system, these metabolites proved, scientifically, what he had consumed.
The body itself becomes the evidence. Okay, finally, a case that's less about high-tech labs and more about just clever observation. The broken jewelry window mystery.
This one was a real head-scratcher. A jewelry store window is smashed. Clearly something was thrown at it. But investigators searched the whole scene, and there's nothing. No rock, no brick, no bullet. The projectile just vanished.
So what was it? Did they throw a block of ice that melted?
Even more clever. The perpetrator threw a piece of glass of the exact same type and thickness as the window.
Oh, wow.
So when the window shattered, the tool he used to break it just blended in. It became indistinguishable from the thousands of other broken shards on the ground. The evidence was hiding in plain sight.
That's incredible. It just shows that the tech doesn't matter if you aren't observing everything with a totally open mind.
Exactly. That's the art behind the science.
So when we pull this all together, what does it mean? It seems like forensic science is this constantly evolving discipline that uses the tiniest little trace, a bug, a number from a physics equation, a speck of arsenic, to build a solid, unshakable link to the truth.
It is. But success isn't just about the fancy labs. It all hinges on that disciplined, careful, rapid collection of the initial evidence. If you mess that up, if the chain of custody breaks or the scene gets contaminated, it's what we call garbage in, garbage out. The best lab in the world can't fix bad evidence.
And that brings us to this new, really volatile frontier. I mean, all of our evidence now is becoming digital. It's on our phones, our smartwatches, our computers. It can be the target of a crime, the tool, or the storage.
And it's so fragile.
So here's the final thought for you to chew on. There's a forensic principle called the law of progressive change, which basically says that evidence degrades and disappears over time. So how are we going to make sure that a crucial, fragile piece of digital data is preserved? What do we as citizens need to understand to protect that new kind of evidence before it's erased forever? That's a profound challenge for the future.